query.
Oh, sweet, okay. So traditional computers, step 1, write some code. Step 2, take some of the code, replace it with binary. Step 3, replace the things you didn't replace with binary, now with binary. Okay, now you have an executable file that you can execute. It's completely binary. Store that in the text section of memory so you don't lose it. And then advance to step 4, which is you take your executable file, you parse it into 32-bit instructions, and then you feed one at a time to the CPU. And then the CPU will take its data and it will update some form of memory, either the L1 cache or a memory or external memory source like a floppy disk or CD or flash drive. Okay, so if you kind of understood that process, you take words, make them binary, execute the binary, put it in memory. We can start to see where traditional computers start to break down, why they're so slow. So there's a lot of latency, which is wasted time between here and here, here and here, here and here and here and here. And then the second reason why traditional computers are not that great is because you can only have one instruction at a time put into the CPU. And if you want the most bang for your buck, you want several instructions being operated on at once. You want high CPU parallelization. So traditional computers are on the decline, unfortunate, but the first evidence of that is Moore's law, which said that every 2 years there should be a double of the number of transistors on a chip. And just for preface, a transistor is like the computational foundational block for a CPU, and the CPU needs transistors to run fast and just run at all. So we're seeing that as the chips are getting smaller, the number of transistors on it is waning every 2 years. So that's the death of Moore's law. And then the second piece of evidence is Shor's algorithm, which is basically a predictive model that describes how fast a computer can perform matrix multiplication. And we find that it predicts that traditional computers will take about 2,000 CPU years just to perform, like, I think it's 232-digit matrix multiplication on n values, whereas a quantum computer would only take 26 hours. And if you didn't understand that, basically, traditional computers are slow, they're not getting faster, and they're reaching that cap on speed. And that kind of motivates why we might want quantum computers. So, for background, normal computers use bits, zeros or ones. That's produced by a voltage difference in a current. Whereas quantum computers have qubits, which can be 0 and 1 at the same time. And it's that superposition that we really desire from quantum computers. So, for example, an n-state qubit can hold 2 to the n pieces of information, whereas a normal bit can only hold 1 piece of information at once. So, and in the lower left, we see our familiar B-field equations, and it stresses the importance of torque, which I'll discuss in the next slide. So this graphic basically just describes, sorry, it's a lot, basically just describes how a magnetic field affects quantum and classical objects. In the first two examples, we see that the magnetic moment, when placed in a magnetic field, will do one of two things. So when you place a magnetic dipole or a current carrying loop in a B field, a torque is produced on it until there's alignment between the magnetic moment and the B field. And it can be in one of two cases: the low energy case, where the magnetic moment is in the same direction as the B field, or the high energy case, where the torque is still 0, but because we have that torque sine of theta, but they're in reverse directions. Now with quantum particles, it's a bit different. You have magnetic moments that there's still a torque exerted on it, but instead of just it simply flipping in the x positive z or positive or negative z direction, you have this angular momentum, which is known as spin. So what happens is, instead of settling down along with the B field, you have this torque that's exerted perpendicular to the angular momentum, and it goes to settle, and then there's another perpendicular torque, and it goes to settle, and another perpendicular torque, until you get this rotation around the B field, and that's known as Lamour's precession, because it's processing around the axis of the B field. And why is this important? Well, qubits, that spin property is what holds the state 0 or 1, which is the information you want on it. So with strategic magnetization, this is how computer scientists like put information on a qubit, essentially, with magnetization. So quantum computers, we talked about traditional computers, we talked about the electrodynamics of qubits. Now we can talk about how a quantum computer works. And there's really just 3 steps, largely. You take qubits and then you induce a magnetic field right here, such that the superposition of the states of the qubits is holding the information you want, resulting of the torque of the B field. And then with that, you have these n-state qubit vectors. And you pass these into qubit gates, such as that, like a multiplication qubit gate. And the qubit gates are essentially like the quantum representation of classical logical gates, like and, not, nor, that operate on Boolean values, but with the extension that qubit gates use with superposition. So it's not just binary, it's 0 and 1, so it kind of accounts for that. And then it performs the operation. You get this resultant vector that is usually a superposition of all possible answer states. And then in the last step, you make a measurement, and the measurement collapses this superposition of states into one, I chose A, but it could have been B, possible answers, and that's your resultant vector. So if anyone's paying attention, we have a problem. Anyone? No, I didn't even see it yet. So we have this big problem because we talk about why we want quantum computing so much, and we want it because there's massive, massive data parallelization, and qubits hold so much information on them. But in this last step, you're essentially reducing all of that parallelization, and a qubit just condenses to a normal classical bit. So, like, what's the point if in the end there's no physical parallelization in this project? And so I was like, oh, well, that's a problem. But if you go back to the idea of Moore's law, you're trying to make chips smaller, and a quantum particle is going to be smaller than the thinnest layer of silicon. So the reason why you can't make chips smaller is because you keep slicing the silicon so thin it's useless, but quantum particles are much smaller, so it's going to help make chips smaller. And then the second reason is the problem that we're currently working on is that if we can find a way to make the arithmetic happen prior to making the measurement, then essentially there's 0 latency or wasted time in arithmetic operations, which is insane. So to explain further, it's basically like you're doing math when no one's looking, and then when you look, the answer's there. And it's got no ALU latency, it's got no calculation time, it's just there, which is exactly what we want. But the problem is, how do we do that? And that's kind of what computer scientists are working on currently. So to review, quantum computers allow for massive data parallelization. They're highly scalable. They help with chip improvements and making them smaller, which kind of helps revamp Moore's law. But the current issue is how do we implement around that state collapse? And then the second issue is kind of like realistic implementations. Currently, quantum computers run at a very low temperature, and that's not realistic for the market. If you want to make it marketable, you should have something that doesn't require a large amount of energy expenditure to regulate the temperature. So that's all I have. Does anyone have any questions? No?
Did you make those pictures?
Yes.
They're so good.
Did anyone? Yeah?
Why does it have to be very low temperature?
What temperature has to be at?
No, like why does it have to be like super low temperature?
I think there's noise introduced when you have higher temperatures with the qubit, which can mess with the spin, and then it's not holding the correct information you need, so the lower temperature helps reduce noise. But if they can figure out a way around that, or like high fault tolerance, which is again the problem they're looking to work on, then we could make them more realistic. We could have quantum laptops. But it's like 50 years in the future, 100 years in the future.
So what in the future would expect
People said 2030 is when we will have a quantum computer that could be used for, like, you know, those big ones in buildings that people only use for like dumb things like matrix multiplication. Yeah. Yeah, we'll only use them for like scientific purposes, but personal ones, no, not anywhere near us.
Any other questions? Thank you. All right, thank you very much. Nice presentation.